Hello everybody, we will continue our Laplace session. In the last part of the previous session, we have ended up with this very important formula, okay, this one. By this formula, we have transformed the differentiation into a multiplication in the frequency domain, which is the Laplace domain. So, from now on, whenever we see a governing equation, which is a differential equation, which governs the system, any engineering system, we will use the Laplace transform as a tool to transform it into the S domain. Okay? So, in the general form, if you have the nth derivative, like that one, this is the general form of the nth derivative. So, if you have nth derivative, you will multiply your Laplace transform by s to the power n. So, f capital of s, this is the Laplace transform of your function. F small of t, this is in the time domain, will be s to the power n multiplied by f of s. All the other terms are depending on initial conditions, because f small of 0, this is just the function that we started with when replacing each t in it and put 0 instead of that t. So this is a number. This is a number depending on the initial condition. So this function is in the new variable s, which is in general, as we said before, s equal a real part plus j, the complex number, which is root minus 1, omega. Omega is a frequency which represents the complex part of this complex number. Okay, the imaginary part of this complex number. So this is about the differentiation and how can we transform it into multiplication. The question now is, what about the integration? If we have an integration in the time domain, how will it be converted to the S domain or the frequency domain? So let's have an example. Now we are asked to get the Laplace transform of the integration from 0 to t to f of tau d tau. As you can notice that the integration from 0 to t. So finally, it will be a function of time, because each tau will be replaced in the limits by t and by d. So we will end up with a function of time. So this is in the t domain, the time domain, and we are asked to get the Laplace transform in the S domain. So let's begin with this substitution. Let g of t equal this integration for simplicity, f of tau d tau. So what about g of 0? G at time 0. So each t will be replaced by 0. So the integration from 0 to 0 equal 0. So g of 0 equals 0. And what about g dash of t? Dash means the derivative. So the derivative of g, so the derivative of an integration will be the function itself. So g dash of t will be f of t. But don't forget that from the initial definition that f capital of S equals the Laplace transform of f small of t. This is by definition. This is from the initial definition. Okay, so now f of S equal Laplace of f of t, and we have proved that f of t equal g dash of t. So this is Laplace of g dash of t. But we have learned together that the Laplace transform of any derivative can be transformed into a multiplication by s. So this is the first derivative, so we can replace it by s, and the Laplace transform of g of t, okay, or g capital of s, okay, this is the Laplace transform of g of t minus initial condition. So it will be g of 0, as we proved before. Okay, so what about g of 0? We have proved that g of 0 equals 0. So this term will be equal to 0. So f of s equal s Laplace transform of g of t. What is g of t? G of t is the integration itself. Okay, we just replaced it by g of t just for simplicity. Okay, so let's return back to our original function, which is the integration from 0 to t f of tau d tau. So what about this term? It can be go to the left hand side. So Laplace transform of the integration of f tau d tau equal f of s divided by s. So this is a very important conclusion, that the integration in the time domain is transformed into just to divide your function, your known function f capital of s by s. So if you have a known function f of t that you know, that you have already known the Laplace transform of it, which is f capital of s, and this function is under the integration sign, so just to divide the known Laplace transform of it by s. Okay. So now the derivative in the time domain is transformed into just a multiplication in the s domain, and the division, and the integration in the time domain is just a simple division by s in the Laplace transform, in the Laplace domain, or the s domain, or the frequency domain. We usually call it frequency domain. Okay? So let's show you another important or very common rule in the Laplace transform. Let's share the screen. Okay. So Laplace transform of t to the power n f of t, this is equal minus 1 to the power n d n f of s by d s to the power. Okay. What does this rule say? It says that if you have a function f of t in the time domain that you know it's Laplace transform f capital of s, and this function is pre-multiplied by t to the power n. So the Laplace transform of the new multiplication will be minus 1 to the power n. This is the same n, the exponent of the t, and have the nth derivative of your obtained Laplace transform of your original function f of t. So let's have the proof of this rule. How can we prove this rule? So let's start with the f of s by ds. Okay. From the definition of f of s, okay, it is the integration from 0 to infinity e to the power negative st times f of t, right? So now we have applied a derivative operator on f of s, so we can apply the same derivative here, d by ds to this function. This is the differentiation under the integration sign, and this is d of t. So now take care that we will take the derivative of this expression with respect to s. So our derivative will be with respect to s, so this t will be constant with respect to the differentiation. So take care. So the derivative of this expression, only we will derive this term, the exponential function only. So the result will be the integration from 0 to infinity. The derivative of this exponential function will be the same, e to the power negative st times what? Times this t under negative sign, because we are differentiating with respect to s. Okay, times f of t is a constant with respect to the current differentiation. Okay, dt. So let's rearrange. So it will be equal minus 1 to pull it out the sign integration. This is the integration sign as it is, e to the power negative st. Okay, so this t will be combined with this one. Okay, so this is the definition of the Laplace transform of this function. So we can rewrite it like this. This is minus 1, okay, Laplace transform of t f of t. So we have finalized the derivation. So now the Laplace transform of t to the power 1 f of t equal minus 1 df of s by ds. Okay. Similarly, Laplace transform of t to the power 2 f of t, we will do the same. We will start with d squared f of s by ds squared, okay, the second derivative of d of s, and this t will be t squared, okay, and this minus 1 will be to the power 2, okay, so this will be equal minus 1 to the power 2 d squared f of s by ds squared, and so on till we reach the final rule that we want to prove, that t to the power n f of t equal minus 1 to the power n dn f of s by dsn. Okay, so from now on, if you see this definition or this expression, a function that you know the derivative, the Laplace transform of it, and this function is re-multiplied by t to the power n, just put minus 1 to the power n, n is the same exponent of this t and take the nth derivative of your known Laplace transform of your original f small t. Another very common rule that we should have to keep in mind that the Laplace transform of t to the power n is equal to the factorial of n divided by s to the power n plus 1. So let's have this proof. This proof is a little bit not straightforward, it is indirect, and we have many proofs for this rule, but I'll choose the easiest one, but it is not, honestly, it is not very easy. So we know that the Laplace transform of f dash of t, we proved before that it is s times the Laplace transform of f of t minus f of 0. Okay. So let's get Laplace transform of f of t to the left hand side. So the Laplace transform of f of t. So we will change the sign of f of 0 and divide by s. So it is 1 over s Laplace transform of f dash of t, the derivative, okay, plus f of 0. So now, if we start with t to the power 1, the Laplace transform of t, so our function f of t, our small f of t, now is t. So we will apply this rule. It will be 1 over s, the Laplace transform of the derivative of the function. The derivative of t is 1, so the Laplace transform of 1, which we have already proved before to be 1 over s, right? Plus f of 0. What's f of 0? F of 0, we have to replace our function t by 0, so it will be 0. Okay, so this will end up with 1 over s squared. So let's go on to see what about the Laplace transform of t squared, t to the power 2. We will apply the same definition. Okay, it will be 1 over s the Laplace transform of the derivative of the function. So our new derivative is Laplace transform is 2 times t, okay, and plus f of 0. F of 0, when you replace t with 0, it will be 0. So just 1 over s Laplace transform of 2t. Okay, so we know that, or we can prove it simply, that Laplace transform of any constant times a function, the constant can be pulled out of the Laplace. So this is very simple. We can prove it quickly from the definition of Laplace transform. So f of s, Laplace transform of f of t, which is f of s, equal the integration from 0 to infinity e to the power negative st times f of t dt. So if you multiply this f of t by any constant, a f of t, for example, so the definition will be like that, times a f of t. And we know that a is a constant, it can be pulled out of the integration. Okay, so it will be something like that, f of t dt. And this is the definition of the Laplace transform, so it is a f of s. So we can simply pull out this 2 outside the Laplace operator. So let's go back to our color. So this will be 2 over s Laplace transform of t that we have already got before, which is 1 over s squared. So our new Laplace will be 2 over s cube. Okay, this is square and this is extra s, so it will be 2 over s cube. And what about Laplace transform of t to the power 3? Will be 1 over s Laplace transform of the derivative of that one, 3 of t squared. Okay, and the initial condition, sure, it will be 0. Okay, so it will be 3 will be pulled out of the Laplace operator over s, this one, Laplace transform of t squared, which we have already got before, to be 2 over s cubed, and so on. The next one will be 4 times 3 times 2 times 1, and the next one will be 5 times 4 times 3 times 2 times 1, and so on. So in the limit we can get this expression. Laplace transform of t to the power n will be n factorial divided by s to the power n plus 1. When we have t to the power 1, here we have s1 plus 1. Here, when we have t to the power 2, we have in the denominator s to the power 2 plus 1, which is 3, and so on. So in general, this is our final rule that we have to keep in mind. Laplace transform of t to the power n equal factorial n divided by s to the power n plus. One of the most popular functions is the trigonometric function sine and cosine. So now we want to know what is the Laplace transform. What is the Laplace transform of sine omega t, and omega is a positive number, any positive number. Okay, so we will apply the definition. It will be the integration from 0 to infinity e to the power negative st sine omega t dt. So let's integrate it by parts. U dv integration of u dv equal uv minus udv. Okay, so now this is u and this is v. So this will equal to, we will integrate this first to have v. Okay, so it will be e to the power negative st divided by negative s. And the other function, which is u, will be put as it is. So it will be sine omega t, and the limits. Don't forget the limits. And don't forget that this integration with respect to time. So this limit will be replacing each t in this expression. Okay, then minus the integration of v du. So The first one will be put as is, and we have another negative here, so this will be plus. So this is S, and this is the integration sign. We are pulling S outside the integration sign because the integration is with respect to dt. So we are interested only in t. Okay, so this is e to the power negative st, and the other term, which is u, will be differentiated with respect to t. Will be the derivative of sine is cosine omega t dt times omega, and the omega is independent of this integration, so it can be pulled out of the integration sign, and the integration limits should be put as it is. Okay, so substituting these limits into t. Okay, so e to the power negative infinity, this will be 0, well, 0. The first substitution. The second substitution, 0 when substituted by this t, when substituted by 0, it will be 1, and this sign will be 0. So 1 times 0 is also 0, so minus 0. This is about the first part of the integration by parts. Plus omega divided by s. Okay, again, we will integrate it by parts using this rule. Knowing that this is u and this is v. Okay, so it will be e to the power negative st divided by negative s. This is the integration of the first part. Okay, and the second part will be put as it is. Then omega t, don't forget the limits from 0 to infinity. Negative omega divided by s. The same. What's this omega? This is when taking the derivative of cosine, it will be negative sign. Okay, so this and we have negative from the definition of the integration by part, and we have negative from the first part, so it will be, we will end up with this negative, and this is the integration. Okay, e to the power negative st, and the denominator is pulled out, and this is the derivative of the second part, which is sine, negative sign, but negative multiplied by the positive, like that one, so it is changed into negative sine omega t times omega. This is the omega of the derivative dt. Okay, take care. What about this part? This is the definition that we have started with. It is the same like this one. So this is the Laplace transform of sine omega t. So we can say that Laplace of sine omega t equal to this term. So let's combine them together. This purple term and that purple term. So it will be Laplace. Let's return back to our original color. It will be Laplace of sine omega t is 1, and that one will be, we will change this sign because we will pull it to the left hand side, so it will be plus omega over s, that one, and it is multiplied again by omega over s, so it will be omega square over s square. Okay, equal what? Equal this term. Okay, so let's substitute. if we substitute with the infinity instead of this t, so e to the power negative infinity will be 0. So the first substitution will be 0. Negative, so let's do it step by step. Okay, so we have first omega over s, this term, okay, times 0, negative, and substituting with 0, so it will be 1 over negative s, and this will be 1. So it will be 1 over negative s. So negative times negative will be positive, and s times s will be s squared. So it will be omega over s squared. So again, let's go back to the right hand side. So the Laplace transform of sine omega t, taking a common denominator, s squared, so it will be s squared plus omega squared equal to omega divided by s squared. So we can cancel this s squared together, and finally we can say that Laplace transform of sine omega t equal omega divided by s squared plus omega squared. So this is a very common rule that we will use frequently in our course. Okay, so if you are asked to get the Laplace transform of sine omega t, don't go through these details unless the question is the proof that the Laplace transform of sine omega t is equal so and so. But if you want the Laplace transform of this one, I think you will keep it in mind, because of the many practices that you will go through in this course. Okay, but as we know that in the exams, usually we will give you a table of these common Laplace transforms. Okay, so don't be worried about keeping everything in mind. Okay, just you will keep it in mind because of practicing. But if you forgot it, you will bring it back from the given table in the exam. Having proved the sine function, let's prove the cosine. So let's have a new page. So the Laplace transform, Laplace transform of cosine omega t. We will go through the same procedure, starting with the definition negative st times our function f of t is a cosine omega t dt. Okay, so let's do it as an integration by parts, and this is u and this is v. So integrating first e to the power negative st divided by s. This is the integration of these exponential functions times u as it is, cosine omega t. Don't forget the limits from 0 to infinity, negative. This is integration sign. Okay, put the first the derivative as it is. So and the s will not be integrated because the integration with respect to t. So we can pull it out divided by s. Okay, and don't forget the sign. Okay, but take care that let's first make it plus. Okay, then times the derivative of cosine. The derivative of cosine is minus sign. So we will again infinity, and this will be negative. Okay, and this is the omega of the derivative, and this is sine omega t dt. Take care that what about this expression? This is the Laplace transform of the sine omega t, which we have already proved to be omega over s squared plus omega squared. So let's substitute. So now let's go back to our original color. Don't forget that the substitution of these limits will give you 1 over s. You can do it quickly. So the e to the power negative infinity equal 0. Okay, and this 0, it will give you 1 over negative s. Okay, and this cosine will give you 1. So finally we will end up to 1 over s negative omega over s times what we have got in our last slide. Okay, so combining them together will give you s times s squared plus omega squared. So this one will be s squared plus omega squared, and this is minus, the denominator is the same, so minus omega squared. So this will cancel this one, and this s will cancel this square. So finally the Laplace transform of cosine omega t equal s divided by s squared plus omega squared. Please take care that the Laplace transform of the sine and cosine is very similar. The only difference that the numerator of the cosine is s and the numerator of the sine is omega.